we'd like to welcome Nassim Haramein to the Architects to the New Paradigm.
Thank you.
So, Nassim Haramein has spent over 30 years researching and discovering connections in physics, mathematics, geometry, cosmology, quantum mechanics, biology, chemistry, as well as anthropology and ancient civilizations. These studies have led to a beard.
Not sure that's a sign of wisdom.
But they've also led Nassim to formulate groundbreaking theories, patented inventions, and also to publish some very important papers in the field of unified physics, which are now gaining worldwide recognition and acceptance. And Nassim founded the Resonance Project Foundation, now known as the Resonance Science Foundation, where he serves as a director of research. His recent documentary film, which I highly recommend, and I just watched a few weeks ago, courtesy of a few friends that are here, The Connected Universe. It explores Nassim's research and implications for humanity. And it really is a beautiful film and really right on mark there. So my hat off to you there.
Thank you. Malcolm Carter did an amazing job.
Well, I have to say, in my friendship with Nassim over the years, it's been an amazing journey to watch what's been going on in his work, you know, from the sidelines a bit. But this is who you would have wanted as your physics professor in high school. That's for sure. So the stage is yours. You have a good time.
Thank you. It's the high school administration that didn't want me. That's a whole other story, isn't it? So it's great to be here in Ashland. Thank you so much for having me, you guys. I love this place. I spent some time here actually working on some devices in some garage. I'm excited to present some of the stuff today. Many of you know my work. How many people know my work here? Oh, and how many people have seen The Connected Universe? Okay, you guys gotta see that movie. I think Malcolm Carter did an amazing job. At least, I mean, the visuals are amazing, if only that. I think the message is important, and we're getting amazing reviews from Hollywood and all this. You know, so if you get a chance, but so I've included some of that stuff in there. But as you know, usually my talks can be like 13 hours with no bathroom breaks. It's the ultimate recycling, right? And so this, you know, this 50 minutes is hard for me. So I will try to get some of the stuff in and try to leave you an impression of where we're at. But I have as well. I'm the director, the executive director of a for-profit corporation called Taurus Tech, and we have sub branches, you know, that are about to output technology out there. So you gotta keep your ears peeled, and this is why I haven't been so much on the front stage, either than touring with the movie around the world. But you know, I haven't been given many talks because I've been kind of clustered in the lab, going oh, you know, and so. You know that thing with the big switch, you know, and lightning and the whole thing. So we have some cool stuff coming your way. That's what I'm trying to tell you. So, and that's why I kind of like dug out the old technological name I give to the resonator. And I wanted to present some of that, but I don't think I'm going to get there tonight or this afternoon, but tomorrow I can follow up with more of the technology. So the idea is to unify the fields. You know, unified field theory in physics is very specific to 4 fields, right? The fields that or the forces that we measure in the universe: gravity, electromagnetic fields, the strong and weak force. And basically they're split in 2 categories, or into 2 theories. One is relativistic equations that deal with cosmology, or galactic structures, stars, planets. And the other one is quantum theory, which deals with, molecules, atoms, subatomic particles. And the 2 don't agree. They just don't. One is saying that the universe is kind of smooth and has these nonlinear functions. And that's Einstein field equation that says that space-time is like a smooth surface, and that when it curves, it produces gravity. And then quantum theory that tells us that no, that space-time is, that things are quantized in linear quantities, little particles or little photons, or little quantas of energy. And so one's saying it's smooth, the other one is saying it's all granular, and so they don't agree. And one of the, and physicists for the longest time were happy with that. Einstein wasn't, but the mainstreamers, and Einstein, literally tried to solve this till the end of his life. When I mean is the end of his life, I'm talking like hours before his death. He's trying to solve these equations, right? And and he couldn't find a solution. And I think only because he didn't have the modern tools we have today and the data that we've received. Otherwise, he would have solved it pretty quickly. It basically was taboo at the time to even say. Foster was witness to that. When people would ask me, what are you working on? And I would say, I'm working on unifying fields. And they would say, we're good. We're good. We've got theory for the small and the theory for the big, and everything's working. Why do you want to unify them? I'd be like, dude, check it out. Big things are made out of small things. So, there should be some kind of theory that kind of works for everything. Unbelievable. And then I would get the look like, well, Einstein didn't figure it out, so dude, And so, but then it became more popular to work on unification. And certainly for me, I started to drill in. So I don't have much time. I'll try to get there. But I tried to drill in. Galaxies are made out of stars, and then atoms make up molecules, and then there's black holes inside galaxies, at the center of galaxies, but as well, the stellar object black holes, and then there is the nuclei of atoms. And I was trying to basically drill down, there must be something that connects the big and the small. Where is the bridge? What, is there some kind of entity or some kind of field or whatever that connects the whole thing? And I was drilling in the physics, and that took me 20 years because it's very convoluted. And so going down, and then I realized that if I solved Einstein's equation for gravity, the solution, most people don't realize that when we solve, to try to figure out the gravitational force between 2 objects or whatever in the universe, and we use Einstein field equations, we actually make the objects that we're trying to solve for little black holes, right? The equation is doing that. The solution to Einstein field equation is a black hole. So, and it says that at the center of the black hole, there's a point called a singularity, and that singularity is of the size of a Planck oscillator. And so what is a Planck oscillator? We'll get to that, but it's a very, 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 very teeny thing, okay? Just think of it that way for now. And it oscillates, exactly. See, the size don't matter. But so this oscillator, okay, is on, the reason it's the smallest thing, it's actually the only natural unit we have. You know, all units are arbitrary, but this one is not, because it is based on gravity and electromagnetic fields. And basically, you can think of it as a photon going through itself. So if a photon is moving at the speed of light, what is the smallest wavelength it could have, right? At the speed of light, it would take the Planck distance to go across itself, right? So it's the smallest thing the electromagnetic field can do if the speed of light is that limitation that produced that grain, right? And so then I looked at the nuclei of atoms, and there was something similar, and that is that when they tried to calculate the amount of energy that's present in the space of an atom, they get this same Planck distance energy level, meaning they get the... So then I started to think, wait, maybe it's all singularities. Like, maybe it's the singularity, right? Singularity, the word kind of says it, right? It's singular, right? So if there's only one singularity that was ever found, then you know that the rest of the universe is singular with that thing, right? If it's singular, right? If it's unified. You guys follow me? All right. Okay. So basically, I started to think that maybe the Planck distance, right, this Planck little oscillator is a fundamental grain, like a holographic pixel of creation. And you know, another 10 years went by. And because the thing is that when we look at reality, we're kind of like being deceived, right? When we look at our world, we say, oh man, there's space, and then there's stuff in the space. And the stuff in the space is pretty solid. It's kind of tough to go through it. And it doesn't want to move if you want to move it. It's kind of resisting, and then when it moves, then it wants to keep going. It's kind of weird, right? And so, what is this stuff in the space? Well, it turns out that stuff that we call the material world is not so material, right? It's really kind of like weird that way. Everything we experience as reality is actually made up of 99.99999% space. The little part that's not space, or the little part we define as something, the material world, is actually just a little oscillation, a little electromagnetic boundary that we are bumping against, and we call that our reality. We call that a stone, an atom, we call that the water, the sand, or a star, a galaxy. And so maybe instead of looking at matter, defining the space, I start to think maybe it's space that defines matter.
It is fascinating to realize that if you remove the empty space in every atom of every human being on the planet and compress it all together, all of humanity would fit into the size of a sugar cube. Granted, it would have the density of a neutron star and weigh approximately 478 million tons, but this helps us to visualize the importance of understanding that every one of us are made of mostly empty space. But as it turns out, that space is not empty.
It was found that space-time at the quantum level is fluctuating with intense energy level, full of dynamic energy components.
We are not only talking about the space outside of our planet, we are talking about the space inside each and every atom of your body. Every single human on this planet has this in common. Regardless of race, color, or religion, we are all individual beings, yet this dynamic energy of the universe is constantly flowing through all of the space inside each one of our atoms, connecting us all.
Thank you. Thank you. Thank you, Captain Picard. This is really an amazing thing, you know, that what we experience as the material world is actually 99.99999% space, right? And it's hard to like comprehend because we experience it as so dense, like, you know, especially in the spiritual community, you know, people are always like, dude, it's so dense down here, I can't handle it, you know. It's like, brah, it's 99.99999% space. So what the heck is the rest of the stuff? Well, the rest of the stuff that is the 0.0000001, that stuff is basically like a little electrostatic field, right? We're not seeing any billiard balls kind of thing down there. That's not happening. Like, you know, particles, like for instance, the proton, all we can say about the proton is that in that region of space, there's a high electrostatic charge, a positive electrostatic charge. We don't see like some kind of like boundary, well, I mean, we see an electrostatic boundary, but that's the only thing. And those electrostatic boundaries are bouncing off each other. And so basically, you know, the space has little bubbles in them. And the bubbles, the electrostatic bubbles, are what you're calling the material world. And you're made out of those things. You're made out of the bubbles, a lot of little bubbles, okay? Like 100 trillion cells are in your body. Think of those as little bubbles, right? 100 trillion cells, so integrate that, right? Like billions of chemical change every second is making sure all these cells are not confused about what they're supposed to do, because any few minutes of confusion would create a very, very, very bad day for you. Right? If there was any decoherence, and to believe that all this is occurring, you know, at random is a remarkable thing. But every one of these cells is made of 100 trillion atoms. So then integrate that. So that's 100 trillion by 100 trillion. So it's very complex, right? And that is mostly space. Okay? These little bubbles, billions and billions and billions and billions of these little bubbles, and they're all highly organized, happy, and doing their job, and, you know, in an amazing way. So that the fact that you're here breathing and listening to this is remarkable. Okay? It's remarkable. And the fact that you think that this stuff around you is really there is even more remarkable. Okay? So basically, it occurred to me early on, and I'm talking when I was a child, that maybe it's the space that we should look at. Instead of thinking that the matter defines the space, maybe it's the space that defines the matter, right? Maybe instead of studying the 0.0000001, we should study the 99.99999, right? Because turns out that that space is not empty at all. Okay? It's not. And many people came to those conclusions. I mean, in quantum physics, it's clear, but let me just say, like, this is the problem, is that we experience from our senses a certain reality, and we assume that that's correct, right? But we only see a very small band of what's going on. Like, for instance, the electromagnetic field. We see a very small band of the electromagnetic field, visible light, right? The rest is completely translucent to us. So, for instance, the space between us right now, it's full of electromagnetic fields, right? It's got radio wave, it's got microwave, it's got, electrostatic fluctuation, it has infrared, it has bloody background radiation from the Big Bang, which never happened, but that's a whole other story. It's remarkable what's going on in the space between you and I right now, right? It's certainly not empty at all. And there's radio waves in there, like all the radio stations, but unless you have a little crystal and you tune it to that exact frequency, you don't hear the music playing on that station, right? I mean, I'm sure there's people in this room, like the psychic kind that are picking up all kinds of stuff like Radio Moscow, but other than that, okay, so you're detuned. So now imagine at the Planck scale, okay, so space, it's got these electromagnetic fields, right? But if you go down, like in the frequency, in the wavelength, and higher in the frequency, you get smaller and smaller and smaller electromagnetic field. Eventually, you get to that point, that Planck scale. Oh, I was like, why am I missing hair? So, what is the, so when you get to that very teeny part, okay, it's imagine there's a lot in there. Well, Einstein came to conclude, and others, that maybe this stuff is what we should pay attention to. So if we want to go back to my presentation.
The great theoretical physicist John Archibald Wheeler, a colleague of Einstein, said, "No point is more central than this, that empty space is not empty. It is the seat of the most violent physics." The theoretical physicist David Bohm explained, "Space is not empty. The universe is not separate from this cosmic sea of energy." And Albert Einstein said, "Physical objects are not in space, but these objects are spatially extended as fields. In this way, the concept of empty space loses its meaning." This underlying background energy that exists everywhere in space is described in physics as the vacuum. What if there was a way to connect to this vacuum energy rather than depleting our natural resources? Humanity is on a course that's unsustainable.
So this is remarkable because so you can imagine it's a very, very small entity, this grain, and what Einstein said. If we can go back to my presentation. That's Einstein tapping in the vacuum there. Is really important. He said physical objects are not in space, but these objects are spatially extended. That means that the material world is an extension of space. In this way, the concept empty space loses its meaning. This is really critical. So these are some of the greatest thinkers on the planet in our history that have told us, like, you guys need to pay attention to the space because the energy in that space is significant. And it really is important to understand that, like, it's not only significant, it's enormous, meaning how small is the Planck? We're going to discuss that in a minute, but you can imagine that you could calculate how much Planck oscillators there is in a centimeter cube of space. And it's a lot. It's a lot. Not just like a lot, but a lot. I really mean that. So let's take a look.
The famous mathematician Benoit Mandelbrot proved that the smaller the unit of measurement that you use, the more accurate your final result. This is important to the work of Nassim Haramein because he uses the Planck units, the smallest unit of measurement available in the universe, in his calculations, which leads to an unprecedented level of accuracy. So, how incredibly small is the Planck unit?
In order to give you a conceptual notion of the relationship in size between the Planck and the proton size, if the Planck was a little grain of sand, then the proton would be the size of the distance between the Earth and Alpha Centaurus, an enormous bubble that spans large amount of space, some 4 light years across.
And then fill it with grains of sand. That's how many Planck units are in the proton. Imagine every grain of sand on the Earth would just be the tiniest speck of the number of Planck units on a proton. Not only does this show how small the Planck unit is, but it also shows how many Planck units fit in a proton. Haramein calculated that all the little Planck pixels add up to all the information of all the other protons in the universe, and that the fluctuation of the Planck oscillators creates the information network that the universe uses to get constant feedback.
So it's teeny, right? So if I took a little, so people say, well, if the space is full of this energy, why can't I feel it? You know, why can't I feel it, right? I forgot about this older technology thing. And, well, of course you can't feel it, like it's just not available to your senses, right? I mean, in fact, and I'm happy to say I just finished publishing my first paper in biophysics. You know, I usually write in physics. I did a paper in biophysics with Dr. Val Baker and William Brown, and we are actually showing mathematically that actually your body, those 100 trillion cells and their cytoskeleton are acting like antennas, tapping into this field of energy, and so although and that is the source of consciousness. And this paper passed peer review and was just published at the Journal of Neuroquantology, so I'm pretty excited about it. And because it's a radical view, it's basically saying that consciousness is not an epiphenomena of your brain, but actually your brain, your stem cell, your microtubule structure, and all of the fluids in your body makes your body act like an antenna interacting with the field of information. And so that consciousness and memory is actually, and this is why the title of the paper is Space Memory Network. I changed the word space-time to space memory because it's more precise. Without memory, no time, right? If you can't remember the moment before, you don't have a concept of time. And so if there's time in the universe, that means that there must be memory on the structure of space, right? And this field which was described by the ancient people as the Akashic record, is then, you know, the memory structure, the hard drive of space-time, right? And so how intense, like how many megabytes is there in this hard drive, right? Well, because the Planck is so teeny, right? If it's a grain of sand and the proton is 40 trillion kilometers in diameter, right? So it's, you know, proton is tiny, okay? It's pretty small. There's 100 trillion in each one of your cells, so it's a small thing, okay? So imagine if you calculate how many of these little Planck oscillators are in a centimeter cube of space, you get 10 to the 94 grams per centimeter cube. Like 10 to the 94, this is 10 with like 93 zeros. Like that's a lot of zeros. You guys might have noticed in your bank account, when you add zeros, things improve rapidly. Okay? If you have like 4 zeros, it's okay. If you have 5, it's better. If you have 6, it's improving very well. And then if you have 7, and so on. And so, like, you know, so imagine 90. So now if I took all the stars in the universe, then he was talking about all of a sudden we've quadrupled the amount of stars in our galaxy alone. Like we were wrong by 4, you know, we were only a quarter in. And then like we probably underestimate the galaxies, but it's a lot of material out there, right? Imagine I stuck all that material inside a centimeter cube of space, how dense that would be, how intensely energetic that centimeter cube of space would be. You would still be missing, you would be at 10 to the 55 grams per centimeter cube. You would still be missing 39 orders of magnitude. You'd be missing 39 zeros to get to the density of the vacuum at the quantum level, like the electromagnetic oscillation that's happening right now in this space and in your body. And what we're saying is that you're literally a tap into that field. You're an expression of that field. This is what Einstein meant. Like, objects are an extension of the space. Okay? And it's all interacting with that same field, with that space. And so when I made these calculations, something really cool happened. This is a paper, this is one of the earlier paper that I was very much chastised for. Lots of tomatoes were thrown, but luckily I'm Italian, so I can make good sauce. So when you calculate the amount of Planck oscillators in a centimeter cube of space, it's cool, but what I wanted to know is how many of those are in the nuclei of an atom, right? That electromagnetic boundary, how many of the little oscillator does it enclose? So I calculated the volume of a little proton structure, and it's very small, you know, 10 to the minus 39 centimeter cube. It's very small. It's a period with 39 zeros, right? It's a very small volume. And then I calculated how many Plancks fit in there, and it turns out that the mass of the universe in terms of Plancks are in there, in a centimeter cube, in a proton volume, right? Now I might explain something because I might have lost you there a little bit in the math. Oscillators, okay, first of all, when you think of an oscillator, everybody tends to visualize like an oscilloscope, you know, going up and down like that. Okay, the universe is not an oscilloscope. There is no waveforms in the universe that are going up and down like this. They don't. They go like this, right? They're vortices. And the Planck oscillator, in fact, you know, the Planck, which is based on the Planck's constants, which is h bar, h over 2 pi, which is h bar, is a little oscillator. It's a little angular momentum. So when you're visualizing the oscillator, don't visualize something going up and down. Visualize something spinning. Okay? Like a little vortex. Now, if you have a little energy, right, you can do E equals mc squared on that energy and figure out the mass of that energy, right? You can change energy to mass since Einstein. Well, you know, when you calculate the energy of one little Planck, you get 10 to the minus 5 grams is the energy of a little Planck. So then you can calculate how many grams of these little Plancks there is in a proton, and the answer is the mass of the universe, or the mass of all the other protons in the universe represented holographically in one of them. Dude. That's what I thought. Because all of a sudden, I had like a mathematical proof that the whole system is one, right? That all information is present in every point. Now, you're made out of these little protons. So if you access that information, all of a sudden, you know, you start to think about the creative process, people that are having, you know, that are able to remote view, all these things, they start to make sense. Right? Where are you getting access to information? So you have a source. The whole thing is entangled. And you can't, and I know it sounds really insane what I'm telling you, but actually some of the best physicists on the planet are coming to that conclusion right now. Okay, you have people like at the top of their profession that are starting to realize particles act like mini black holes, and they seem to be entangled through wormholes interaction between particles. That there's micro wormholes that form in that structure of space-time at the quantum level, and it connects all the particles together. You know entanglement? You guys understand entanglement? I mean, we measure that in laboratories. That means that you can take a particle over here, and the other particle can be on the other side of the world, and if you tickle this one, the other one acts like it's being tickled. And, you know, we are doing it now with larger objects like diamonds. We can entangle diamonds. And then you're in laboratory, you're hitting this diamond with a laser, and the other one over there is acting like it's being hit by the laser. Okay? And so, like, this is actually a fact that things can be entangled in this. And however, you know, the idea currently is that, well, there's things that are entangled, but there's particles that are not. Right? Because they have to come out of the same atom to be entangled and so on. But there's other things like their relationship. But now, okay, so you see a particle here and it doesn't appear to be entangled with anything else. Well, that particle is not limited to your observation. The universe is not stuck with you. Because if it was, I would be in big trouble, right? Because so this whole thing about, I mean, I don't really have time, but I want to tell you, this whole thing about the double slit experiment and the Copenhagen interpretation is fundamentally wrong. And now physicists are finally coming to that. It's fundamentally wrong. Like, you know, if you put a cat in a box, right, it's not in a superposition state, like live and dead, until you open the box and then you observe it and all of a sudden it claps into the waveform of a live or a dead cat. It's not. The universe is not confused about the state of the cat because you are. It just isn't. It's not awaiting your observation. Because what about the flea on the cat? What about the microbe in the box? It's not because you put the cat in the box that it's isolated from the rest of the universe. It's not requiring the human. It's not. If the tree falls in the forest and nobody's there to hear it, does it make a noise? Of course. Of course. The rest of the universe is not requiring the human in the forest going, oh. 10 minutes. Oh my God. So, that was a divergence. Let me just say that the double-slit experiment has now been explained with fluid dynamics, showing very clearly that particles are in a field. And of course, if particles are in a field, when they move, they make waves. So it's a particle and a wave at the same time, but not in some esoteric. And of course, if you put an object in there to measure the particle, that object makes waves and interfere with the waves that the particle is making. So it appears like it does another thing. And you go, oh my God, when I observe it, it changed. Yeah. Just because you're making waves. But everything else is making waves too. It's not like human-centric. Right? The whole thing is talking to the whole thing. So when a particle is entangled, if the particle is under our observation, we see it being entangled. But if the particle is on the other side of the world or the universe, right? It's entangled, but when we tickle this one, we can't measure the other one, so we think it's not entangled. You see what I'm saying? So the whole thing is connected, and the whole thing is talking to each other. So then I calculated, how is it talking? I'm going to have to skip that. Sorry. We'll get to it tomorrow. But, you know, so I took a black hole and I said, okay, well, how many particles of these little Planck oscillators? So think of the little Planck oscillator as like a little termination of a Planck wormhole, right? That connects the black holes together. And I calculated how many are on the surface. They're a large number, 10 to the 79. And then, you know, and this is a well-known black hole. And then how many on the inside? And, you know, all tiled in a special way. And, you know, the equation is only true for that specific tiling, by the way. And then I thought, so imagine this. You have all this information on the inside, but you are limited by the amount of information that can come through the surface. So there's an energy potential that you've created because you have a difference between the inside and the outside, right? You guys get that? Okay, well, it's pretty straightforward. I can't believe it took me 30 years to figure that out. But imagine, so I did a ratio. I wanted to know what's the relationship, and then I multiply the ratio of the information inside to the surface by 1 Planck mass to get the mass of the ratio, right? The energy of the relationship. That makes sense? When I did that, I got the exact mass of the black hole. That is, I solved for Einstein field equation without using Einstein field equations. I solved for gravity, the gravitational mass of the black hole, by using Planck quantum fluctuation. So I was using quantum theory to solve for gravity. You guys start to see the bridge building between the two theories? And so of course, then I was excited. I was like, and it's exact. And so it's saying something different than Einstein. Einstein said space-time is curving to make gravity, like if you put a ball on a trampoline surface and another ball around it will look like it's attracted. Think of a tub of water, you pull the plug, and you see the surface of the water curving. If you put a rubber ducky in there, it starts to orbit, right? It looks like a little gravitational field, right? Well, what I discovered is what Einstein described as the curvature, which is really hard to describe, you need tensor equation and all this stuff, is correct, but it's a secondary effect of the particles of water in the tub all co-orbiting in that region of space. You guys see what I'm saying? So out further from the top, from the hole in the top, the water is not co-orbiting, so the rubber ducky is not being attracted. But when you put it where the water is co-orbiting, where the particles are co-orbiting, then it starts to be attracted. So basically, it was saying, yeah, Einstein was correct about the curvature of space-time, but it's because space-time is granulate at the very fine level of the Planck length, because that it is doing this gravitational effect. So then I applied that to a proton, because if I had quantum gravity, then it should work from cosmology to atomic level, right? If I was going to unify it. And so I applied it there, and I counted the number on top. Check it out. You know, it's a lot. Counted the number inside, 10 to the 60th inside. So remember, 10 to the 60th, right? Multiplied by the mass of each Planck will give you the mass of the number of Planck inside the proton. So 10 to the minus 5 multiplied by 10 to the 60th is going to be 10 to the 55 grams, which is the mass of the universe. So we got the mass of the universe in the equation. How insane is that? I'm calculating the mass of a proton, one proton, right? By using the influence of all other protons in the universe on the one guy. Right? The mass of a proton is 10 to the minus 24. It's a very small mass. And my equation includes the mass of the universe in it. How precise, you know, when I was doing these calculations, people thought, this is insane. You're not going to get a precise value if you're using huge numbers, right? And then when you do the cal, right? So you do the ratio between the two multiplied by the Planck mass, and it outputted the mass of the proton with the precision of 0.0012 of the co-data value that's measured in laboratory. It's like, whoa! I was hoping it was going to be within like an order of magnitude. I would have been happy, right? Like, you know, I was blown away. And I was like, took me like 3 weeks or 2 weeks to like come down from my pink cloud of like, oh my God kind of deal, right? It worked out so good. I was blown away. Well, you gotta understand, I mean, these are very simple concepts and simple equations, but it took me a long time to get there. You wouldn't believe the insanity of the amount of mathematics that eventually got me there. But, you know, after I came down from my pink cloud, I'm like, but why am I off by 0.0012? And I was like, oh, that's kind of bugging me now. And it took me a while, but then I realized by manipulating the algebra that this equations predicted a radius, because remember, I'm counting the number of Plancks in there, so I'm using the radius that's given in laboratory for the radius of the proton. I realized my equation didn't agree with that. And so I predicted, this is the same equation rearranged to give me a radius, right? So in the paper, I predicted what the true radius of the proton should be, and it was 4% smaller than what the mainstream, you know, measurements were in laboratory. And so I had the choice to say my equation is wrong, or you guys are wrong. And you all know me by now. I was pretty confident because my equation was exact for cosmological objects, right? And it was outputting exactly, if I use that radius, it was outputting exactly the gravitational coupling constant, the interaction time. I mean, all sorts of fundamental values were coming out just right. So I knew, like, the radius had to be correct, because if I used that radius, everything came out right. So I predicted in the paper that that radius would be found eventually with higher resolution experiment. And you know, this, and I thought maybe I'll be dead by the time they are able to do these experiments. You know, I may never know if it was correct. But then, unknown to me, in Switzerland, in an accelerator, they were trying to measure the radius of the proton more precisely. And they published like I published these equations, it just happened to be December 21st, 2012. And 2 months later, they published the result of that experiment in Switzerland, and it turned out that the radius of the proton they got was 4% smaller than previously. And now my equation predicted a radius within 0.00036 of the value measured in laboratory in Switzerland. And of course, then the mainstream standard model is off by 4%. So I just want to say, my value is inside, the theoretical value is inside one standard deviation of the experiment. That means it's inside the margin of error. So this 0.00036 is actually them getting closer to the value, not me being off, right? Just so we're clear. So tomorrow I'd like to talk to you more about this, but as well like what it means to consciousness in your life and how it can change the way you see the universe, see yourself and your relation to it, but as well how we use the same equation now to solve for all the electrons in the in the table of elements. And it's exact, it's very, very, very precise. And so now we can accommodate, we can show that all the material world emerged from this fundamental field that we're all interacting with. Thank you so much, everybody.
Oh, man. Thank you. Wow. This is why we had you last, because we all got to get to the cocktail party to kind of come down from this. Oh, yeah. This is such juicy stuff, Nassim. Thanks for rolling it out to us. And tomorrow is going to be a chance to really expand on this some more. So
thank you so much.
Thank you so much.
Thank you, everybody.